at B. I hope it will work this time because my last recording did not work very well, but let's begin.
That's
We have 2 out of 5. I guess it all depends on the frame of reference, like 5 p.m. But we'll have to make do. So we'll start with like collisions. Solve an equation. An example of plastic collision. We have two particles with masses here M1 and 2 and gamma factor. Gamma describes particle 1, while particle 2 is at rest. Two is at rest. After collision, stick together. They'll change the color. It's a bit, especially in the camera, it's very hard to see. They stick together. Move the gamma factor with gamma over 2. What is mass ratio? M1 over M2. Yeah, M1 over M2. That's what we need to solve.
gamma is the velocity.
But gamma is the, well, gamma is the velocity. It's 1 over 1 minus vector.
Oh, okay.
Yeah. Well, we'll work in this class that's equal in the convention that's C equals 1, just because it simplifies some of the equations later. Okay, so we need to find out the ratio between 1 and 2. Just to describe what's going on here, we have particle M1, moving here with the gamma, particle M2, they collide. Then we have some particle with some unknown mass M, which is not necessarily equal M1 plus M2, since we are talking about special relativity, is conservation of mass, not of energy. And that moves, because of conservation of momentum, in the same direction with gamma. That's the fact. Got one thing, the limit that assume gamma greater, much greater than 1. Like we are talking about relativity speeds. Okay. So how do we do it? We write the momentum before momentum solution. write the form momentum before and after the collision. After so what is it before? Nobody has known. So
Yes, sir.
what is it before in you?
Yes.
What is the energy?
And
Okay,
this-
for one particle, if we have only one particle,
Yeah.
assuming that C equals 1,
Okay.
and it equals to gamma m,
Yes.
gamma m.
V. Yes.
Here it's C, but
Yes. C equals 1.
okay, this is for one particle.
Yes.
What do we do? What do we have in our system?
Gamma M and 0.
Okay, what is before the collision? What is the for particle 1?
Wait,
I didn't.
Huh? It's exactly it's this exactly.
Exactly. Yeah.
So leave it as D. We want relativity moment. So we have gamma m1 to gamma m1. What is it for particle 2?
gamma and 2 and 0.
0.
Yes.
This is like this is the vector. This is 3 coordinates. What is here?
Oh.
Huh?
M2.
M2.
Emptiness.
Gamma equals 1 because the particle is at rest. Okay. What do we have after the collision? Theta. So just a minute, just for the completeness. This equals for collision to gamma m1 plus 2. Here it's like gamma m1. It's the sum of the total energy. What do we have after the collision? We have a particle with some
Gamma.
unknown mass, big M,
Gamma by
and
2.
our gamma factor is
Gamma by 2.
gamma over.
Yeah. Half of gamma.
Over 2, and gamma over 2, and let's call it V tag. V tag is a function of gamma over 2. Okay?
Yeah.
Very bad luck with maybe this one will work.
Okay, so since we have energy momentum information, energy momentum.
This
Momentum acceleration. Yeah. E U equals to E times U. So it gives us two equations. Gamma m1 plus m2 equals to gamma over 2. And that we have gamma m1v equals to gamma over 2 and theta. divide 2 by 1. Yes. We get theta equals to gamma m1 v gamma m1 plus m2. Okay. How do we continue from here? Any ideas?
You have to calculate mass ratio.
Yeah, we have like some functions of m1 and m2.
Yes.
And we have like this v and v tag, but we know v and v tag as functions of gamma.
Yes.
So what we need to do now is to express them as functions of gamma.
Okay.
So v, okay, gamma equals to 1 over the square of 1 minus v squared, or v over c squared, c relative to 1. So this, if we square both sides, we get 1 over 1 squared. Then we get v squared equals to, I think it's like this. It gets to v equals to gamma minus 1 over gamma squared. You can just follow the equation. Again, v tag equals to gamma squared minus 4 over gamma squared. It's just the same, but we put gamma over 2 squared and then multiply by 4, upside down. So, okay, so let's continue from here. Yeah. Gamma squared minus 4 over gamma squared equals to, okay, let's multiply by with the denominator, gamma m1 plus m2 equals to gamma m1 and v, like gamma squared minus 1 gamma. Now we want to write. Okay, so we have gamma m1 gamma squared minus 1 over gamma minus gamma squared minus 4 over gamma squared. And that equals to gamma squared minus 4 over gamma squared and 2. So we get m1 over m2 equals to it's a long expression here. Gamma squared minus 4, gamma squared minus 1, minus gamma squared minus 4. This. Okay. Now we use the assumption that gamma is much greater than 1. And we can simplify it even more.
Yes.
So we get gamma is greater than 1. Here, gamma 1 minus gamma 2 over square. Yeah. Gamma minus 1 square. Gamma 1 over half gamma square. And minus 1 plus 2 gamma square. This one gamma. So, okay, this is not that interesting. So we have 1. Here we have 1 over gamma. Here we have like 2 minus half equals 2.
And you have minus 1.
What?
1 minus 1.
No, 1 minus 1 cancel out.
Yeah, so like
This equals 2. 2 over gamma. Yeah, it's over 1 squared. So we have. Is that okay?
Yeah.
So that equals to M1 over. Any questions about it?
No one wants to be in our Zoom.
You have time for elastic collision example. Collision. That's before particle 1 lights particle 2 and comes. Particle 2 rest. This time we scatter different angles. Theta 1, theta 2. What are the angles? That's functions. Functions of E1, E1, E2, E2, E1 tag, E1 tag, E2 tag, E2 tag. That's what I tried to do on Sunday before this thing started drilling. We have the incoming energy and momentum, outgoing energy and momentum. We want to find out the scattering angles. Okay. Let's just roll this out. 1, 2, E1, E1. This is like E2 is 0, and E1 equals to M2, and E2 equals to M2. Then it scatters theta 1, M1, E1 tag, E1 tag. The particle 2, this is theta 2, scatterers with P2 tag, P2 tag. Okay. So the question is pretty clear. So we use again energy momentum conservation. We have P1U plus P2U equals to P1 tag mu plus P2 tag U. And now we want to isolate which one of them? Isolate P2 tag. Yeah. So that is equivalent to P2 tag equals to P1 mu P2 mu minus P1 tag mu. And now we square the equation.
But P2 mu is 0.
Yeah, I forgot to write.
No, P2 mu is 0. No? Because it doesn't move.
It's a four momentum, so
The
it
four
equals to, yeah. P2
Oh, okay. So M2
yeah,
divided.
it's these three coordinates.
Okay.
And we square the equation. So we get minus m2 squared. Why is the minus?
Yes, of course, it's the
That's an important.
from the
If we square, we don't just square like mathematics.
No.
We square like a vector. We multiply it by
yes,
the code.
yes. So P mu comes out to be minus m square c square.
Yeah, so P2 mu, P2 mu. It's basically M2 0 0 0 0 0 times
Yeah.
vectors, so it's not exactly, it's just one representation equals to M2 minus M2 0 0 0 times M2 0 0 0 again minus M2 squared. This is the real way to do it is eta mu mu.
Yes, exactly.
And P2 mu, P2. That's where we got minus. So we got minus M2 squared equals to, it's algebra here. P1 squared is minus M1 squared. This is also minus M1 squared. So we get it twice. Yeah. Okay, let's do it step by step. Plus.
Here also we are considering c equals 1, right?
What?
Here also we are considering c equals 1.
C equals 1. Yeah. Throughout C equals 1. P1 u, P2 u, minus M2 squared. So P1 u P1 tag mu minus 1 squared minus P2 u P1 tag mu. Upstairs, so we don't need to.
Right.
Here I forgot to do. Okay. Is it clear why it's like
Yes.
Yeah, that's just P tag, P2 tag mu is all by
here? No, here not that.
no, on the left.
Yeah, this is P2 squared. P2 tag squared.
Find 0 on the velocity.
And no. It's always for a given particle, P mu is always minus n squared. Always.
Okay.
Like you get gamma factors and okay, should have shown that. if P mu equals to gamma n P. So if you do minus gamma square, okay, we have minus gamma square m square always. We have gamma square minus m square. Minus gamma square m square minus 1 plus v squared, which is exactly minus gamma.
Okay.
Minus gamma square.
Okay.
So that always happens.
Maybe we did not cover it last week, so yeah. Okay, so we got all this long equation. Now we can basically write it down. Okay, this comes twice. This
Cancels with this. So we have m1 square equals to p1 u p2 u plus minus p1 u p1 w minus p2 u p1 w. Okay. Now we're going to make use of p2u that we know its exact form.
okay.
Can I ask another question?
Yeah.
Here the mass and the start and at the end are the same for each particle?
Yeah, it's elastic collision. Particles,
Mass stays the same.
they change like particle momentum and energy, but the mass will remain the same. Okay, so we know P2U, so we get m1 squared equals 2. Basically, this is, we know P1U, let's write everything. So P1U equals to P1 U1, P2 U equals to M2 P0, P1W equals to P1W, P1W. Okay?
Yes.
So now we know that P1U, P2U, it's like at U, P1U, P2U. Now we have minus U1 and 2. For a similar reason, if we had the tag, it's like minus P tag, like P1 tag, U, P2, U, minus P1 tag, and 2. But P1 W, P1 U equals to minus P1 tag plus P1 tag, which gives us minus P1 tag plus P1 tag cosine, which is what we need. Now we just substitute into star, we get m1 squared equals to minus e1 and 2. Here we have plus e1 dot minus e1 dot plus I plus dot 2 get the cosine of 1 equals to e1 dot 2 minus e1 2 plus e1 dot this divided by p1 which is what we needed. Minus m1. Yeah, seems legit. In a similar manner, you can have cosine derivative.
Just verify I'm not doing something that I'm probably given a homework assignment. Don't want to do that.
Okay. You studied about stress energy tensor and dust, right?
Yeah.
So dust and stress energy. So how does the tensor look in like in the frame of the dust? Okay, in the frame of the dust, frame dust, like in the restaurant, we have T mu nu, it says, yeah, T mu nu is equals to 1.
Okay, P, and others are 0.
Rest is 0.
Yes.
Right?
Yeah.
What do we have?
The frame with velocity v, that T mu nu equals to eta mu rho p plus rho plus p times u nu. You recall that?
Yes.
You know our scalar, right?
Yeah. want to make one remark about collisions. You're going to have like, if you look at homework number 2, you have like questions about collisions. Basically, you have to use two things. One, that P mu times P, like P mu square, or like square with our metric, always equals to minus m square, and the conservation of the vectors, not conservation of masses or anything like this. Okay. In fragment velocity, where u is where u say equals 1 is gamma.
And does that mean that all the dust moves at velocity v or something moves?
Yeah, like you have.
I'm in math and I see the dust.
You have the rest frame of the dust, then you start running or flying in a very fast
Everything
pace.
goes.
Dust, so you measure like all the dust particles move move in relation to you, so they get like Lorentz factors. Okay, so the energy changes. Or the momentum. Let's say you look at one dust particle and you look at its energy on its momentum 4 vector. So it starts like so. The Lorentz transformation for boost general direction in a general direction is given by gamma 0, 0 equals to gamma 0 I equals to gamma I0 equals to gamma I. The gamma Ij equals to delta Ij plus Ij over v square gamma minus 1. Okay. So that we'll see. Rest frame. S E tensor the dust transforms to general frame. To the general. Is it clear? I'm asking clear? No. We have stress energy tensor. We have a tensor in some rest frame. And we have a tensor in some frame moving with velocity v. Yes. Now, how do we transform tensors? We multiply them by the transformation method. Yes. In our case, because we're still in special relativity, we're using the Lorentz method, yes, which is given by components of this form. So what we want to get is like to get the components in this form by multiplying Lorentz transformation with this energy tensor in the rest frame. Maybe I should do a short short recap of how do you do tensor manipulation? Or
No, it's
No,
okay.
it is fine, but the question,
what does it mean?
yeah, exactly. The question is,
Okay. In stress energy tensor, it's a way to analyze the components. Yeah. I think it should have been covered in the lecture. I don't know if you understood it or stuff already got it. If you have like a stress energy tensor,
Okay.
this component is energy density.
yes,
Density.
yeah,
This component is mental density. Density. This is energy current, energy flow current.
yeah.
Flow current.
Still one or three.
This is like momentum flow current.
Okay, yes.
Flow current. Now, I don't remember around it. Generally, it's symmetric. Like, and if it's not symmetric, you can transform it to symmetric form. I don't remember the exact derivation of all the fine details in it. But for us, like momentum density and energy flow current is the same.
Yes.
So let's say I have some stress energy. Let's say I was in dust, rest frame, then I start moving towards it. So I see like all the energy density changed because like the same as particle that is boosted has different energy. Okay. And for the same reason, also all the particles have some momentum, which is let's say I run this way, so everything around me has a momentum this way. So I measure some kind of momentum flow. Now the intuition for momentum flow current is like, let's say I have a momentum, like some particle is moving to the x direction, but I'm moving to the y, so how much do I feel like, let's say I'm in some, current, and we have like something like this, like the current diminishes, say move in the y direction. So this is like some kind of definition of the momentum flow. If I move in a certain direction, if I move in a certain direction, like I said,
Suppose
like
we
after a
can take
moment,
the two-dimensional flow, like suppose this is the time dimension and this is the x direction, and suppose a particle which is at rest is moving in the time direction. So at any moment of a particular time, we can see how many the lines are passing through it. That will give me the current, how much the current is flowing through that particular moment of time. You didn't.
no, I understand. Just like I
It's
don't
like
know.
suppose, yeah, this is the time axis and this is the x-axis. Suppose we are taking the two dimension,
Yeah,
and many particles which are at the rest along the x-axis, and they are at the rest. So then the what is that line called? No, but
the wall line.
yes, exactly. The world line will be a straight line because yeah, of course. The particles are at the rest, we can take the world line of the particle.
Yeah.
So at any instant of time, because my y-axis is the time, so at any time axis, my particular time, I can see how many number of particles are passing.
Yeah, but that's
That will give
momentum.
the current. Yes, exactly. That's what I'm saying. Yeah.
Yeah, but that's not. That's momentum.
Yeah, exactly. The similar way you can say suppose the particles are moving along the x direction. So
No, here I'm talking about special directions because this part involves only like special coordinates,
yes,
like x and y, for example.
yeah.
I'm trying to think of some intuition for it.
No, exactly. But we cannot think for the whole 4 dimension because it will be too complicated. So we can make for the 2 dimension or 3 dimension. We can intuitively consider as okay,
so
this will happen for this 4 dimension as well.
This area of the map.
Yes, exactly. Because for
Zero
four
R.
dimension, it will be like a cubical shape. We will have to consider for number of particles which are moving through particular face of a cube. Like suppose if you are considering
This
x, yeah, y.
This is simple intuition, I think. Like,
How can we think of another way?
like how does momentum density
Changes. Yes, exactly.
along the axis?
Yes.
So your momentum is a vector, and then we can move on other directions, and I'm just asking how much does this vector change?
Okay.
This is like the momentum. It has, well, momentum by definition it depends on time. Like
Yes.
you're looking at velocity, so it's space versus time. Yeah, I'm just trying to give intuition for this.
Okay.
I'll see if I have like a better intuition. Anyway, so what I want to say, this is a more general form after I boosted. And then I want to see, this is, now it's just algebra. I just want to take this tensor, multiply it by the Lorentz matrix, and get this tensor. Like I just want to get the so we do it for each component or for each type of so T00 frame. I'll call it like I'll call this V, this R, like boosted inverse. Okay. T00V equals to gamma 0 alpha, gamma 0 beta, T alpha beta, S frame. Now I have to sum over all alpha and beta, but I know that alpha and beta have to be equal because all these components are zero.
Yes.
I mean, generally I can sum of different alphas and betas because we get zero here.
Yeah.
So we get lambda 0, 0, lambda 0, 0, 1, plus lambda 0, 1, lambda 0, 1, p, plus lambda 0, 2, lambda 0, 2, p, plus lambda 0, 3, lambda 0, 3. This is very simple. Gives us gamma square rho plus gamma square v square. The other hand, T00 B is equal to eta 00 B plus rho plus P U0 U0 U before equals to gamma gamma. So we have minus P plus rho plus P and gamma squared. So we have gamma squared rho, which is good. We have gamma squared minus 1 P. What is gamma squared minus 1? Gamma squared. We have gamma squared rho, 4 plus 1 over v squared, 1 minus 1 over v squared, 1 over v squared, a. You can easily see that equals v squared gamma squared. Okay. I'll do another component, and the last component I can do just exercise, like the last time. Also, it's the hardest, so making myself an easy job. So T0I equals to lambda 0 alpha, lambda I beta, T alpha beta. And the rest. Again, here it equals to lambda 0, 0, lambda I 0, T log plus P times T 0, 1, lambda 0, 1, lambda I 1 plus lambda 0, 2, lambda I 2 plus lambda 0, 3, lambda I 3. That gives us gamma square VI. If we look at the components that I just erased from the board. Like that equals to gamma, equals to gamma VI. So we get gamma square VI. That's a bit more complicated. We have P. We have that lambda ij equals to delta ij plus some other expression. So let's first look at the other expression. Okay. Reminder, lambda ij equals to delta ij plus vi vj v square gamma square 1 square gamma 1. Okay. So first we can ignore the delta, and we have some all over, right?
How did you get this thing?
This I gave you as
Okay. Okay, it is.
If you
Yes,
want
yes,
to redevelop it, you have to compose rotations over a boost.
okay.
Because you're looking at the boost at the general direction, so you have to rotate this axis to the x-axis, boost along the x-axis, and rotate it back.
Okay.
That's like that. To the right. So we have this part, but we sum over VI and VJ, right? Overall IJ. So we have 0, 1, 0, 2, 0, 3. So we have each one of them gives me gamma VI. Gamma VJ. So, okay, let's do one more step. That equals to, should have written this before, gamma lambda ij, right? That's just what's written here. Up to the fact that I sum two lower indices, but if I use if I use Latin and not Greek, it's only special parts and special relativity, it's identity vectors. So now we have gamma square I rho plus B. Now we have D. That equals to gamma Vj. So we have, let's look at this part. So we have Vi, Vj over V square of this times gamma Vj, gamma minus 1 plus P delta Ij gamma Vj. Okay? I just substitute all of these here.
Yeah.
So first I relate to this part. So now we have equals to gamma I rho plus gamma I p gamma minus 1 because Vj, we have like Vj divided by v squared, we get 1. Plus the gamma vi. That gives us gamma squared vi full plus gamma squared vi. So this corresponds to this. On the other hand, we have T0IB equals to eta 0IB 0 plus P plus rho U0 U pi. That gives us that is 0 plus P plus rho gamma times gamma pi, which is exactly what we have written above. Okay. For T ij b equals to lambda 0 I alpha lambda j beta T alpha beta rest. This is I think it's a good exercise in like tensor calculation. Nothing very complicated except maybe the meaning of things, which you can solve the question without understanding. But you should understand them. That's part of the course. But it's also part of the course to know how to do calculations.
Can I ask a question?
Just
Yeah. Okay, once you had the I upper and the other one lower I. Does it matter?
Okay, we said it before, and I will repeat it again. Generally, in this course, if I would look at it slowly, I'll find out where I switch it from upper to lower. It should be, if it's upper on one side, it should be upper on the other side. And it's very important. Like,
Because
it's not equal. It's like generally not equal. But now we're in special relativity. And our metric is very simple. It's eta mu nu equals to -1, 1, 1, 1. Okay?
Yeah.
And I and j, okay, if I have mu, it runs over 0, 1, 2, 3. If I have I, or A, like generally in Latin letters, it runs over 1, 2, 3. 1, 2, 3 is the identity matrix. So if I, as long as we're still in special relativity, if I do the switch of I up and low, it's not correct. I will try to avoid it. I shouldn't avoid it here. But the answer will remain the same. It's a bit of abuse of rotation on my side, but the answer is correct. Like just I think it's the sense. Okay. Now we'll have how did special relativity start? What was the motivation for it? As I've mentioned it in the first lecture.
There is no ether present that Michelson-Morley experiment.
What are the first equations ever written in special relativity?
Maxwell's equation.
Maxwell's equation. So So we need to know how to write Maxwell's equation in tensor. Otherwise, if we can't write the Maxwell's equation in all the language that we formulated in the past few weeks, then special relativity is probably theory. So, okay, what are the Maxwell's equations? Maxwell's equations. What are the equations? You can give me their names, you can give me the equation itself.
Gauss.
Gauss.
Yes.
How do I write Gauss?
Well, I don't remember, means they are kind of a Gaussian unit and the other unit, so I confuse with
Give
it.
me an any unit.
Del dot T rho upon epsilon naught.
The divergence of E
Yes, of course, that's
equals to charge density.
yeah.
Or charge density over C or epsilon
Yeah,
zero.
that's why, yeah, different kinds of units, yes.
Okay. Another equation.
Del dot B 0.
Okay. The divergence of B, 0, which is equivalent to saying there are no magnetic monopoles.
Monopoles exist,
Okay.
yes.
Two more equations. We have like the dot product.
And the cross products.
Okay, what are the cross products?
Yeah, del cross E is mu naught J plus mu naught epsilon naught dou E by del
Del
dot T.
cross B or E?
No, del cross B.
B.
Del cross B, yeah.
Cross B equals to J.
Okay, yeah. I prefer saying in mu naught J plus mu naught epsilon naught.
Plus, yeah,
That's the same.
up to unit.
Yes,
up to,
excellent.
yeah. Which means that magnetic fields are created by currents,
Yes.
magnetic currents, and
Modified Faraday's.
yeah, it has like, how do they call it? Like the, definitely in English, like the Maxwell's, you call it like current something. Like the
Displacement current.
Displacement.
Displacement current, that capital D term, yes.
Yeah, E equals to
Minus of, yeah, minus
which is
by
also
dt.
known as the Faraday's law.
Yes.
Okay. And then now we define. Okay, another important thing about it.
Yes.
You know that if we have, let's say, some wire charged, and now we boost alongside that direction. What do we have in the booster system?
I can repeat.
No, we have like at the rest frame, a charged wire.
Okay.
So we have some field, electric field E, and we don't have any magnetic field, right?
Okay.
Because we don't have any current. Now we boost alongside the certain direction. What do we get? I boosted alongside this direction.
Yeah.
So basically all the wire carries some current,
Yes.
right? So we get like some field, like we get this field, right?
Yes, of course. Yeah.
And we may get
Exactly.
some field
Okay.
E because of the excess charge, but
Yes, yes. Okay.
depends on that. So what do we know now? That magnetic field or electric field alone cannot be like some 4 vector or something. Like if you boost, you have some exchange between magnetic and electric field. So therefore, E and B need to be combined, into a single tensor. We define such tensor F alpha beta equals to F0I equals to EI, Fij equals to epsilon I, J, K, dk. And F of beta equals 2 minus F. So I can't trace it.
Let's hope that one of this will work well. Otherwise,
Let's write it in terms of metrics. By the way, have you encountered this tensor? Like,
Yeah.
Yes.
it's not the first time we see this. Fij equals to 0, 0, 0, 0, di, and dx, dy, z, minus dx, minus dy, minus dz. Now let's take 1, 2, 1, 2, 3, dz, minus dy, dx. Here we have minus bz, dy, minus bx. There is another easy way to remember this tensor. You remember like potential? So a way to remember is, and we know using potentials. You also see it in like quantum mechanics or something. No? And we have E equals to minus rod phi.
Okay, yeah.
Yeah. Yeah, no, this is first. The B equals to curl of A.
Yes.
For these are the potentials.
Yes.
We define for potential. A mu up to factors of C. It's like phi, A. Then F mu. I think they write it with lowercase as usually. F mu equals to d mu A mu minus d mu A mu. Now, if you develop it like each component, you'll actually get this tensor. So that's an easy way to develop it. And if you take a course in quantum field theory, this is how they define the photon field. Like there are fields, like we have like a field of the electron and a field of the photon, basically the forward.
Is QFT available here?
Now,
No, I don't think so. Is QFT available here?
QFT available.
Means
I think Asaf
no.
teaches it in, or he has a course in the articles.
Okay. Okay.
So it's
Like advanced quantum.
No, advanced quantum mechanics also will not go in this. That's the entirely different course. Quantum field theory.
okay. And now Maxwell's equations. Why don't we start? Covariant form Maxwell's equation. Max equations. One is like F alpha beta. Now notice
Symbol.
this
Notation.
Yeah.
Yes.
notation.
Yeah.
Like it equals d alpha.
Yes.
beta.
Yes. Yeah.
That equals to minus j beta, which will get to j. So that is equivalent to
Okay. Continuity. Yeah.
db equals rho and curl b equals j without the extra term. Yeah. Plus
Yes.
another one is epsilon alpha beta gamma delta, which is a four generalization of the other Relativity tensor.
Yes.
So in three dimensions, three coordinates. Gamma delta beta equals 0. That is equivalent with v 0 curl b equals to minus db delta now j u equals to rho j, which is kind of encompasses the drawing I had on the board before, where you have like some charge density and you boost, you get the copies, and vice versa. You want to see how like one of the equations equals to one of these equations? Okay. Choose your favorite equation of the four. No, actually, trying to see one that will.
Can you the second one because I also always get
This?
Yeah.
Okay, so let's try to prove this one. Let's choose alpha equals 0. 0 is the time part. Yes. Epsilon 0. Beta gamma delta f gamma delta dot b. Okay?
Yes.
This equals 0. So we can do basically this one equals to 0, 1, 2, 3 f 2, 3 dot 1 plus 0, 1, 3, 2 f 3, 2 dot 1 plus epsilon 0, 2, 1, 3 f 1, 3 dot 2 plus epsilon 0, 2, 2, 3, 1 f and 3, 1 dot 2 plus epsilon 0, 3, 1, 2 f 1, 2 dot 3 plus epsilon 0, 3, 2, 1 f 2, 1 dot 3. Okay, this is term by term.
Yes.
Now, this is 1. What is f23 dot 1? It's dbx to be, no, dbx, yeah, dbx to x. dx dx.
right?
I didn't
Okay,
get that.
let's do one F23 tag 1 plus F3 minus.
I didn't get that tag sign you are using. So what does that thing mean? Actually, I got confused with that. F23 tag 1 means which component are you talking about?
I'll get to it soon.
Okay.
Just write this.
Okay.
Okay, what is this? This is minus 1, 0, 1, 3, 2. I switch them. Minus F3 to F1. And here we switch. This is plus and minus. And this is minus because we switch 1, 2. And minus F1, 3, and 2. This is plus because we just switched to the last one. Again, F1, 2. Here, this is like 1, 2, 0, 2. It was 1, 2, 3, 0, so it's minus F1, 2, 3 plus F2, 1. This is minus because 1, 2.
Three, no, it's plus, right?
Let's switch 0 with 3 with 2. It's like one switch. Two switches, I think. It should be like this.
So, okay.
Worst case, I will get the wrong answer later.
Yes.
Yeah. No. That's close. Yeah.
Confusion.
Okay, what is F3? You want
So we go to the matrix.
Yeah.
Cancel.
Yes, F230.
It's like BX, right?
Yeah. Minus
Okay.
BX.
BX. And what is 1? 1 is X.
Oh,
So that's for your question. That
Okay,
means
okay,
D1
yeah, got it.
F3, which equals dx dx. We have dx dx minus dx minus dx, okay, minus dy minus dy plus dy dy plus dz dz minus dz minus dz. What you have here, 2 times 2. We know that that equals 0. That's exactly, yeah, no.
I want to.
Now, if you will choose alpha equals I, you will get one component of this equation. If you choose like alpha equals 1, for example, you get the x component of this equation.
Yes, exactly.
And if you choose, then you have this equations. I think if you choose here b equals 0, you get the first equation. If you choose like beta equals ijk, you get the ijk components of this equation.
Okay.
Okay, we have 5 minutes. I'll write for you the stress energy tensor for the electromagnetic field, and we can run with this. Very well.
That's good.
Okay. 2 more things. Electromagnetic forces. Borrowing form. That form. So we know what is the electromagnetic force. F equals dP to dt. That's like in the more familiar Newtonian dynamics. Equals to E, which is the charge. E
Q
plus V equals V. That's electromagnetic force. That's electric force. This is the
Magnet,
force.
yes.
Okay. The variant form is F alpha, which is defined to be dp alpha d tau
Yes.
over time equals to E F alpha gamma U gamma. Like UT for U0, UT equals 1.
Yes.
And then we have like basically the electric field. And if you have like some component, you get like if you have like components of the velocity, like VI for example, you get like cross product to
Yes.
the
Okay.
definition of the and we have stress energy tensor. So rest. How does it tomorrow? T N beta equals to F alpha gamma F beta gamma minus 1 over 4 beta alpha beta F gamma delta F gamma delta. What it is. Which gives us T00 electromagnetism equals to 1/2 E squared plus B squared, which is the energy density of electric and magnetic field.
Yes.
Removing factors of permittivity and
Permeability,
of the
yes.
vacuum.
Yeah.
And this like 0 M equals to E equals B, which is the
Pointing vector, yes.
Okay, that's it for today.
Let's just hope that the recording went well.